Hi, my name is Thales, and I'm going to talk about accelerated quantum control with limited resources. Our goal is to realize fast quantum gates with high fidelity. One of the main advantages of fast gates is the fact that if the gate time is much smaller than the dissipation time, then dissipation effects on the dynamics will be very small. However, fast gates are not so simple to realize, since they might require controls that are hard to implement in the lab, and also they can introduce other kinds of errors. For instance, when dealing with a two-level system, one typically neglects counter-rotating terms. However, depending on how fast the gate is, those terms might become important. Let us be a bit more precise about the kind of problem that we want to attack. We want to realize a unitary operation on a quantum system so that we take the system from its initial state psi to a final state psi f. And we also assume that the Hamiltonian of the system is given by this expression, where H0 is the ideal Hamiltonian that generates precisely the dynamics that we would like to have. It takes the system from psi to psi f through this blue path in the Hilbert space. And V is an unavoidable perturbation that spoils the dynamics. It takes the system through this orange path in the Hilbert space, and we end up in a final state which is not the state that we would like to have. We want to find a correction Hamiltonian W, and it's important that this correction Hamiltonian cancels only the average effects of V on the dynamics. This means that our system might take a completely different path in the Hilbert space, but it will end up in the correct final state. In order to find the W operator, we are going to use the so-called Magnus expansion. The Magnus expansion allows us to rewrite complicated time-ordered exponentials that appear in the definition of evolution operators as simply the exponential of the sum of other operators. And using this property, one can show which condition a first-order correction Hamiltonian must fulfill in order to correct the dynamics. Here we see that the average effect of W precisely cancels the average effect of the V Hamiltonian. Another important aspect is that this equation imposes no restriction on the specific time dependence of the W operator. This means that we have an infinite number of solutions for this equation, and we can restrict ourselves only to the solutions that are experimentally feasible. Experimental limitations, like controls that are not accessible or bandwidth limitations, can be easily incorporated in our method. As an application of our method, we consider the problem of the leakage in a transmon qubit. A transmon can be understood as an anharmonic oscillator, and we assume here that only the first three levels of this oscillator contribute to the dynamics. Therefore, we obtain the following Hamiltonian, where H0 gives us full control over the first two levels, and V of t represents the leakage to the third level. If one performs a Hadamard gate in this system without any kind of correction, these are the fidelity levels that one can achieve. The faster the gate, the higher is the fidelity error. Therefore, if one wants to achieve faster gates, it is indeed necessary to use some sort of correction. In order to correct the leakage problem in a transmon qubit, we consider the following correction Hamiltonian. This is simply a driving term in which two pulse envelopes, Gx and Gy, couple to the transmon with different phases. Therefore, our correction Hamiltonian represents simply a change in the shape of the original pulse. In the literature, one can find other pulse shaping techniques applied to the transmon leakage problem, perhaps the most popular being drag. Drag, however, does not correct 0 to 2 transitions, and this limits its performance. Apart from choosing the specific form of the correction Hamiltonian, we also impose some constraints on the envelope functions Gx and Gy. Both gx and gy are 0 at the initial and the final times, and they can also be written as a truncated Fourier series. Note that the maximum value of k, which we call kmax, is related to the bandwidth of the envelope functions, and we can choose the value of kmax such that bandwidth limitations in experiments are respected. The coefficients a and b that appear in the expression of the envelope functions are the free parameters that we want to find such that the final state fidelity is increased. If we proceed with the method discussed here, it turns out that the non-trivial optimization problem that we attack here is converted in a simple system of linear equations on the coefficients a and b. Here we finally show the results of the fidelity error for a Hadamard gate when our correction method is used. In the blue curve, no correction is used. In the green curve, a second-order Magnus correction is used, while in the red curve, a sixth-order Magnus correction is used. We also plot the results of a fifth-order drag. We can see that the results of the sixth-order Magnus correction greatly exceeds the results of the drag correction. With that, we hoped that we convinced you that our method allows one to perform fast gates with high fidelities. We stress that our method can be used in other situations, for instance to correct the effects of counter-rotating terms in two-level systems or to increase the fidelity in snap gates. My talk ends here. Thank you.